Hello everyone, and welcome back to another Unboxing Tomorrow adventure in electronics, robotics, and communication systems, where today we're going to be revisiting the topic of the AVR microcontroller. It's been a while since I made that earlier video, and since then, Microchip Technology, who now owns the Atmel brand, has rebranded Atmel Studio into Microchip Studio. Fortunately, this change is mostly in name only, so I've put today's video together for programmers and hardware developers who are still looking to get started. In fact, I would call this a good starting point, even if you have no prior experience with the AVR, and I'm going to cover the basic material requirements, including a few passive components to get the AVR running, and the system to actually program it. To recap, an AVR is an 8-bit microcontroller, and you can program it using coding languages such as C, C++, or assembly. For transparency, I'm not affiliated with Microchip Technology or Atmel, other than being an ordinary user, since the year 2001. Since then, the AVR portfolio has grown, and you can use them for anything from robots to control systems or human interfaces. This command line, which is for the drone project, was done entirely using just an AVR ATtiny 87-XU. To get started on your own, you'll have to get, of course, the AVR itself, along with supporting systems. But because I have no idea what you want to build, your first step will be to define the application and do it in certain terms so that you can define what the AVR will be doing. This initial step might involve developing a system-level block diagram and then adding details as the job progresses. The purpose of step 1 is to define the requirements and narrow your search for an AVR. Your choice is your choice, but I will mention that the most common AVRs that I stock here for this blog include the entry-level ATtiny 2313, the very popular Atmega 328P, which you can find on Arduino Uno, the general-purpose Atmega 8535 and the Atmega 16, and strangely enough, the LIN-bus-compatible ATtiny 87XU. Step 2 is to define the system voltage. Usually this voltage depends on what you're going to have available from your power supply, battery, or voltage regulator. Most AVRs will accept a range of voltages that is centered somewhere near 5, 3.3, 2.7, or 1.8 volts. The higher voltages also tend to use the most energy. You can use an online search, like the ones I recently covered, and apply their search filters until you have a list that meets your specifications. Step 3 is to choose an IC package. The available options include DIP packages, which are the most beginner-friendly, to leadless devices, such as QFNs or BGAs, which are the smallest, but require advanced soldering techniques. Packages containing the names SOT, SOIC, PLCC, TQFP, TSSOP, or basically anything else with SSOP included, tend to lie somewhere in the middle. In other words, they're not extremely easy to solder, but you do get used to it, and if nothing else, they are easier to inspect. Arduino Uno uses the DIP package, which seems like a decent starting point. The next step is to choose an exact part number. Picking an exact device can be daunting even after the filtering, but hopefully the earlier steps have narrowed the field. AVR part numbers are systematically named, with the initial 6 or 7 letters indicating the product family name. The next cluster of digits, and sometimes lettering, will indicate the family code. Remaining digits indicate the speed, the IC packaging type, and whether or not the device is sold on bulk reels. The most prominent families are ATtiny, which focuses on basic peripherals and low cost, the Atmega series, which will have more peripherals and a hardware multiplier, and the ATxMega series, which has high-end and advanced peripherals, such as DMA or direct memory access. There are way too many to cover in this video, so I'll refer you to the official Peripheral Integration Quick Reference Guide, which is a one-page document that summarizes every device. Once you have an exact AVR in mind, you're going to need a special tool to go between the AVR and your computer so that you can program it. In the Microchip Studio application, the programming device is simply called the tool, and the AVR is called the device. As of summer 2021, a reliable way to tell which tool works with your AVR is to go to the official webpage, search for the AVR that you want, look around for an area titled Emulators and Debuggers, and investigate it until you find the latest list. The tools that are most relevant to this blog include the officially discontinued but still popular AVR ISP Mark II, which you can buy these days from a third party. I also have the newer AT-Atmel ICE, which works on Atmel AVRs, and even Atmel ARM Cortex. In this blog series, I'll be using both of them interchangeably, and even a few I haven't mentioned, so if that sounds helpful, or if you have a special request, let me know in the comments, and I'll see what I can do. The programming tool will connect to your computer using a USB cable, most of the time anyway, and the opposite end of the tool will have a specialized cabling system known as ISP, or in-system programming. The ISP ribbon will break out into 6 smaller wires, and you will need to have those 6 wires connected to the AVR as shown in the diagram here. Wires MISO, MOSI, and Sync can be directly wired to their corresponding pins on the AVR. The same is true for the ground, and usually VCC. The reset line is a bit different because it requires a pull-up resistor providing a path to VCC and a pull-down capacitor providing a path to ground. The resistor value is usually somewhere between 10K and 100K, and you can find a range of recommended values in the AVR's own datasheet. For the pull-down capacitor, 100 nanofarads typically seems to work, especially if the capacitor is ceramic. Speaking of ceramic caps, you will also need to use an additional one as a bypass capacitor by connecting it directly between VCC and ground, and doing so as close to the VCC pin as you can manage. For AVR models that contain multiple VCC pins, you will need a bypass for every VCC pin. The reason is outside the scope of this talk, but suffice it to say it will help you avoid random device resets caused by electrical noise and interference. The ideal value will depend on your application and the circuit board, but 100 nanofarads is a very common starting point. Finally, we have the clock. Modern day AVRs, and by this I'm excluding the older AT90 series, give you the option of using an internal oscillator or attaching something external such as a crystal or a ceramic resonator. For the AVRs that I listed today, the internal oscillator operates somewhere near 8 MHz, and by default the device is probably going to reduce it to 1 MHz to reduce its power consumption. The exact frequency of the internal oscillator is going to depend on the temperature of the die and the operating voltage of your AVR, so it can be quite unpredictable, and at the very least you should calibrate it, which I will cover in a future video. Ceramic resonators tend to be more accurate than the internal oscillator, and a crystal tends to be more accurate than the ceramic. If you decide to purchase a crystal, you will also need to pair it with 2 identical capacitors, and those capacitors are going to provide both pins a path to ground. The purpose is to provide a phase shift that will allow the crystal to start and sustain its oscillation. Getting the value wrong will prevent this, and you will need to reference the crystal's datasheet in order to get the right value. And fair warning, this value will not be titled C load, which is a common mistake. The schematic you see here is pretty typical of an AVR with bare minimum hardware. In other words, we have a programming interface, signal conditioning for the reset line, a bypass capacitor, and a optional crystal. In the next video, I'm going to be covering how to install Microchip Studio and a few things that have changed since Atmel Studio 7. But if you're feeling confident, you can go ahead and go to the official website and install it right away. If you find this sort of thing useful, be sure to like and share the video. This helps me figure out what people are interested in, and it will help the channel in general. As usual, this is made possible thanks to support from Patreon, where I am also posting frequent updates on the drone project, something that might actually fly by year's end, and there is also a monthly poll and lessons learned on technical builds like this one. And this is also made possible thanks to my affiliates, Satoshi Labs, maker of the Trezor cryptocurrency wallet, and TorGuard online privacy protection services. TorGuard is a service that I use to reduce my online exposure to data collection and constant online tracking. It's easy to use, and to learn more you can see the link in the video description for information on TorGuard VPN or virtual private networks, business VPN, private email, and even physical VPN routers. Stay posted for the next video in electronics, robotics, and communication systems, and as always, have a great day.